In this video, we're going to look at systems of linear equations, and we're going to talk about a very specific example where we have three variables in each equation. Now, much of what we talked about in our previous section where we were solving systems of linear equations in two variables doesn't exactly translate because in the previous section, two lines could either intersect at a single point, or they could be parallel to one another, or they could represent the same line, meaning that the two equations were equivalent. When we're talking about equations in three variables, we're talking about lines that exist in three-dimensional space. So there are more possible scenarios. Two lines could indeed intersect at a single point. In that case, the point has an ordered triple for its location: an x-coordinate, a y-coordinate, and a z-coordinate, which represents that third dimension. But lines can also miss each other, and that can happen either if the two lines are parallel, meaning they're on the same surface, but they never intersect, or they can also be skew, which is a concept that's really kind of difficult to explain when we're doing this video. So let's look at the mechanics of how to solve systems of equations in three variables, but I do encourage you to look at some additional videos for background so that you can understand conceptually what is being represented. The process for solving a system of equations in three variables is very similar. It just takes a lot of additional careful detail. Let's look at the following system, and I'm going to need to create more space here, so I'm going to scroll up. For ease of reference, I'm going to label this as equation 1, this as equation 2, and this as equation 3. That way, as we modify these, it's easier to understand which equation we're talking about. First, you're going to choose which of the three variables you would like to eliminate first. For ease, I'm going to try to eliminate the x variable first. So to eliminate x, I'm going to combine the first two equations as follows. I'm going to multiply the first equation by -3. Then I'm going to add it to equation 2. So when we multiply the first equation by -3, we have -3x plus 9y minus 3 times z equals -39. I didn't show all the work here, but you may want to do that on your own paper. Now we're going to add this to equation 2. Equation 2 we're going to write unchanged. Notice that when I add the multiple of equation 1 to the original equation 2, the x variable disappears because -3x plus 3x is 0. Let's finish adding the rest of the terms. I'm going to call this equation 4. Now, I have to somehow use equation 3 because it was part of the original system. I'm going to try to do something similar here where I eliminate the x variable by combining equation 3 to either a multiple of equation 1 or a multiple of equation 2. It's not going to matter. It really is a matter of preference. So, to eliminate x, I'm going to multiply equation 1 by -1. Then I'm going to add that to equation 3. When I multiply the first equation by -1, I get -x plus 3 times y minus z is equal to -13. I'm going to write equation 3 unchanged. here we have that negative x plus x is 0, as intended. 3y plus negative 3y is also 0. That wasn't intended, but it's nice. And then negative z plus 3z is equal to 2z. That means that I can, I made a mistake there. Negative 13 plus 11 is not 11, is it? I'm going to go ahead and write that as a negative 2. We get that z is equal to negative 1. Now, I need to somehow solve for y and then for x. Notice how equation 4 has only only y and z. Only y and z. Let's go back to equation 4, and I'm going to rewrite it. 10 times y minus 6 times whatever z stands for is equal to negative 34. Well, now I know that z stands for negative 1. So I can make that back substitution. So I have 10 times y plus 6 equals negative 34, or 10 times y is equal to negative 34 minus 6 will be negative 40. Dividing both sides by 10, we get that y is equal to negative 4. So I have the value of z, I have the value of y. I can substitute these values into any of the original equations to then solve for x. So let's go ahead and use equation 1. In equation 1, we have that x minus 3 times y plus z is equal to 13. I know that the value of y is negative 4. Let me substitute that in. I also know the value of z is negative 1. So let me simplify what I have in order to solve for x. I have x plus 12 minus 1 equals 13. X plus 11 is equal to 13. Subtracting 11 from both sides, we get that x is equal to 2. Since I have a value for x and a value for y and a value for z, I have found that there is one solution to the system, and it is the ordered triple: 2 for x, negative 4 for y, and negative 1 for z. Now this is a triple. It represents a single point in three-dimensional space. So I'm going to put the curly brackets around this ordered triple to indicate that this is the one solution to the system.